This is the lecture for the Chapter 11 notes. We're going to cover the topics of intermolecular forces, and then we will cover some properties of liquids and properties of solids. We start with the definition of what an intermolecular force is, and that's the weak force that holds solids and liquid particles together. So if you take a look at this diagram, you can see the strength of these intermolecular forces compared to the strength of an ionic or covalent bond. We have a hydrogen chloride particle attracted to another hydrogen chloride particle. The covalent bond is what connects the hydrogen to the chlorine, and that takes 431 kilojoules to break that bond. And we're looking at the intermolecular attraction being a lot weaker. It only takes 16 kilojoules to separate one particle from another. So the intermolecular forces are what allows particles to condense into liquids or to freeze into solids. So we're going to be looking at the intermolecular forces in this unit. And if you look at a substance when it melts or boils, it's the intermolecular forces that are broken, not the covalent bonds. So I use an analogy of a shirt and a sock. If you put a shirt and a sock in a dryer and have it slosh around, the static cling of the shirt sticking to the sock is the intermolecular attraction, versus if you were to take a piece of thread and sew the sock to the shirt, that would be representing something like a covalent bond. So it's a weak static cling attraction between molecules that are described as intermolecular forces. Now, one of the characteristics of a molecule that represents the strength of the intermolecular force is the boiling point. If you have a higher boiling point, that indicates a strong amount of attractive forces. And if you had a high melting point, that would also reflect a strong attractive force between the particles in the substance. And there are four basic types of intermolecular forces, and we're going to have slides on each one of these. The first one is the ion dipole force, and just to give you a quick overview, the ion dipole force is between an ionic particle, like a cation or an anion, and a polar molecule. And the dipole force is exactly what you might think. It's between two polar molecules. London dispersion forces exist between all molecules, and they're caused by electrons randomly moving throughout the electron cloud. And the last type of intermolecular force is called a hydrogen bond, and that's a special type. So we're going to start with the ion dipole force. This force exists between an ionic particle and a polar molecule. And as you see in the diagram, we have a polar molecule with one side being slightly positive and the other side being slightly negative, and it's attracted to a cation and an anion. And obviously you would have the opposite charges attracting each other. So the negative side of the dipole is attracted to the cation and the positive side is attracted to the anion. When salt dissolves in water, what actually happens is that you have an interaction between the negative side of the water molecule and the cation, being the sodium, and you have the positive hydrogen part of the molecule surrounding the chloride ion, and so that rips the salt apart. So the ionic bonds between the positive and negative charges cannot withstand the attractive force between the ion and the dipole. And so we say that these ions are hydrated. And if you click on the link at the top of the page, you can see a flash movie of salt dissolving, and it describes the process in quite a good amount of detail. The second intermolecular force is called a dipole-dipole force. Sometimes I nickname it dip-dip, just to talk faster. So anyway, it exists between two polar molecules. It's weaker than the ion dipole force, and if you have two molecules with about the same mass and size, they have about the same amount of London dispersion force. But the dipole-dipole force is going to increase if you have more of a polar molecule. So the picture shows a positive and negative side. These are partial positive and negative sides of a polar molecule attracting another partial negative of another polar molecule. So that's why these forces are weaker than the ion dipole force. These are only partial charges attracting each other, not full-blown cation positive charges and negative anion charges. So anyway, if you look at the chart, these compounds listed in the chart have all about the same molecular weight. So the London dispersion forces between these molecules are about the same. But the dipole moment, that's how much it's polarized, the dipole moment increases, and you can see that the boiling point increases. So again, the amount of stickiness between the molecules is related to the boiling point. So if you have more dipole-dipole force, you're going to have a higher boiling. Now the next force of interaction is the London dispersion force. This intermolecular force exists between all molecules, and it's caused by a creation of a temporary instantaneous dipole. And if you don't know what that is, if you click on the link, it'll show you a flash animation of this temporary dipole that gets created. The electrons around the nucleus of one atom become slightly bulged or asymmetrical, and that side of the molecule will be slightly negative and the other side is going to become slightly positive. And then you have these London dispersion forces that are created from the slightly positive and negative side of the molecule or atom interacting with one another. And so in the diagram that you see on the bottom, the helium atom on the left has a nucleus that's attracting the helium atom on the right's electrons. So those electrons come closer to helium atom number 1. And that causes slightly positive and negative charges to form in each particle, and then they have an instantaneous temporary dipole that gets created. And this is a much weaker force than the dipole-dipole force. Now we're going to compare the strength of London dispersion forces within nonpolar molecules. If you have a larger nonpolar molecule, you're going to have a greater number of electrons and it becomes more polarizable. That means it's easier to create these instantaneous dipoles with more electrons flying around. So if you compare the boiling point of fluorine to, let's say, iodine, since fluorine has a lower molecular weight, it has less electrons, and therefore it has less London dispersion forces than iodine. And then if you look at the noble gases, the trend is the same. As the molecular weight of the noble gases increase, the boiling points increase. And since an element, a pure single atom, would only have London dispersion forces, that is the reason the boiling point is higher. So if I asked you, why does helium have a higher boiling point than xenon, you wouldn't simply say because the molecular weight is greater. You would say because the London dispersion forces are greater, because xenon is more polarizable. Another factor that increases the London dispersion forces is the shape of the molecule. If you have a greater surface area for a nonpolar molecule, it's going to have more area of contact for these dispersion forces to exist. So London dispersion forces between a spherical nonpolar molecule like neopentane is going to have a lower attractive force compared to a molecule that's a little longer and spread out like regular pentane. The N-pentane is the one that is more linear, so its boiling point is going to be a little bit higher because there's more area for this London dispersion force to exist compared to neopentane, which is sort of balled up pentane. The less surface area has less. Now the last case of intermolecular attractions is the hydrogen bonding. That's a special case of dipole-dipole force, and by experiments scientists noticed that compounds that contain hydrogen-fluorine bonds or hydrogen-oxygen bonds or hydrogen-nitrogen bonds have abnormally high boiling points. That means the intermolecular forces between these particles is extra strong. Now, to create a hydrogen bond, you need two things. You need hydrogen bonded to a small, highly electronegative element, and that limits us to just 3, fluorine, oxygen, or nitrogen. And you also need an unshared electron pair. That would be called a lone pair or a non-bonding pair, and that's going to occur on the fluorine, oxygen, and nitrogen of the other molecule. And what happens is that there's an attraction between the hydrogen of one molecule and the FO or N of the other molecule. And so we're going to look at some diagrams of this. So I like the little cartoon. The name's bond, hydrogen bond. And if you look at the picture, that little dotted line that runs from one water molecule to another is described as the hydrogen bond. It's the oxygen of one molecule attracting the hydrogen of the other. In picture number 2, we have 2 ammonia molecules. The hydrogen of one is attracted to the lone pair on the nitrogen of another. And then in picture number 3, there's a water molecule attracting an ammonia molecule. And again, you see the electron pair of the oxygen attracted to the hydrogen. Now, why are hydrogen bonds so crazy strong? Well, you have an extrapolar molecule when you have hydrogens and oxygens, or hydrogens and nitrogens, or H's and F's bonded together. So the hydrogen is extra positive, and the oxygen, especially with lone pairs or nitrogens or fluorines with lone pairs, that's an extra negative. So there's a little extra boost in the dipole-dipole attraction. Now, what does the chart show? The chart shows that nonpolar molecules generally have lower boiling points than polar molecules, but if you look at where water is located on this chart, even though it has about the same molecular mass of CH4, it has an abnormally high boiling point. So we would normally see a trend of nonpolar molecules having lower boiling points than polar molecules, but H2O is just a freak. That extra freaky strong hydrogen bond is what connects your DNA molecules to each other. The double helix is connected with a double hydrogen bond on the base pairs adenine and thymine, and a triple hydrogen bond on your base pairs guanine and cytosine. And you can see that in each case we have a hydrogen of one molecule attracting the oxygen of another, and the hydrogen is bonded to a nitrogen or oxygen. So if you look at adenine, we have a NH attracted to the oxygen of thymine, or we have a NH on the thymine attracted to a lone pair of electrons on the nitrogen. Down below in cytosine and guanine, we have again an NH bond, and those are attracted to oxygen lone pairs or nitrogen lone pairs. So it's pretty cool that there's 5 hydrogen bonds that you're seeing in the base pairs AT and GC. Pretty awesome. So this slide shows how intermolecular forces are related to dissolving. So there's a phrase called like dissolves like, and that simply means that polar solutes dissolve in polar solvents and nonpolar things dissolve nonpolar things. And so the diagram shows hexane trying to mix with water. Well, hexane molecules are nonpolar and they have only London dispersion forces between them. So they're attracted to each other due to London dispersion forces. Where the water molecules have hydrogen bonding capabilities. So they also have London dispersion, they also have dipole-dipole forces, but they also have those extra strong hydrogen bonds. And so the water molecules are going to be more attracted to each other because of the dip-dip forces and the LD forces that exist between those particles. And the hexane molecules will not be able to mix down into the water molecules because they don't have the similar type of bonding. This page shows water molecules hydrogen bonding to each other in the first circle. In the middle, they show methanol molecules hydrogen bonding to each other. And in the third picture, if you mix water and methanol, they will freely mix because both of them have that intermolecular force similarity. They both have the hydrogen bonding capabilities, so they can completely mix with each other in any proportion. And I like the cartoon. It says, "Help, help, I'm dissolving." And the other bear says, "But bears are insoluble." And the bear in the water says, "That's easy for you to say. You're not polar." Ha ha ha, you get it? Hey, that's for you, Slifer. All right, now we're going to change gears and look at properties of liquids. The first property of a liquid we're going to discuss is viscosity. Now, viscosity is the resistance of a liquid to flow. The thicker a liquid is, the more viscous it would be. So syrup is very viscous. If you heat up wax, it gets less viscous as it gets hotter. It gets thinner and thinner, and it runs easier. So the thicker the liquid, the more viscosity. Well, intermolecular attractions relate to viscosity. If you have a lot of intermolecular attractions, the liquid will become more viscous. And you can see in this chart, there's hexane all the way down to decane. These are nonpolar molecules. They only have London dispersion forces existing between them. As the molecule gets heavier and heavier and heavier, the viscosity increases as well. This viscosity characteristic will typically increase as the temperature gets colder. So if you get a colder liquid, it doesn't flow as well. As the temperature increases, this flowing ability, this viscosity will go down. So that's an inverse relation. Now, another property of a liquid is surface tension. Surface tension acts as a thin skin that allows bugs to kind of walk across the water. They can't poke through the intermolecular attraction between the liquid particles. And if you have more surface tension, that means there's a stronger intermolecular force between those. Now, here's some fun little facts. Soap makes water wetter. That's a phrase that a lot of scientists like to say. And what does that mean? Well, soap makes water wetter is describing the effect of the soap on the water. It reduces the surface tension. It's capable of breaking up the hydrogen bonding between the water molecules so that water can soak into a fabric or it can start attacking dirt or something like that. So instead of the water attracting to itself, it attracts other stuff. And the second fun little fact is soap doesn't kill germs. Instead, what happens is that germs are attracted to the soap suds from intermolecular attractions, and then they're just washed down the drain. Oh, by the way, the only type of soap that would kill germs is an antibacterial soap. But regular old soap that doesn't say antibacterial just washes them down the drain. Now, moving on, it says normally oil and water don't mix. So they separate into different layers, and the soap actually breaks the oil up into smaller droplets, and it surrounds the oil, and so it can mix with the water. And so the diagram shows what a soap molecule looks like. One end is hydrophilic, which means it's the polar part that's attracted to water, and the other end of the soap molecule, it's a really long chain that's hydrophobic. It's nonpolar. So there's a polar and nonpolar end, which is kind of cool. The nonpolar end attracts the oil. The polar end is attracted to the water. So these soap particles surround an oil particle and allows it to separate from the big bulky oil particle that might be on your pants or a shirt or something like that, and then the soap is allowed to wash it away. So this is how soap cleans your hands. If you get a drop of grease on your hands or something like that and you suds it up with soap, the one end of the soap molecule attracts the oil, and the other end is attracted to the water, and it suspends the oil into the water, and then you just rinse it down the drain. Now we're going to look at phase changes in energy. This is a topic that we've already covered in this year. We're looking at the change in heat, that's the enthalpy to vaporize something versus the enthalpy to melt it. So we have the heat of vaporization and the heat of fusion. So it looks like the vaporization is a lot larger than the heat of fusion as shown in the picture. So the heat of fusion of butane, that's the heat to melt it, is only 5 kilojoules per mole, where the heat to vaporize it is 24. You can see that trend in all of the other compounds. The heat to melt it, the heat of fusion, is always less than the heat of vaporization, and that's because when you melt something, you're only breaking some of the intermolecular attractions, but when you boil a substance, you're breaking all of the intermolecular attractions. So it would make sense that you would have more heat to vaporize something than to just melt it. Now let's talk about liquefying a gas. In order to get a gas to liquefy, you have to get the particles close together and moving slow enough that the intermolecular attraction sticks them together in clumps and it turns it from a gas into a liquid. So the highest possible temperature that you can have for a substance to remain a liquid, regardless of how much pressure you're applying to it, is called the critical temperature. So there's a minimum amount of temperature, or should I say a maximum amount. There's a maximum amount of temperature that you have for a particular liquid, and if you're above that temperature, it's automatically going to boil. It's going to be a gas. So the critical pressure is the pressure that you need to apply to that substance in order to keep it as a liquid. So let's look at some examples in this table. Look at water's critical temperature. It's very, very high compared to the other ones because it has the most intermolecular attraction. So the intermolecular attraction is increasing and the critical temperature will increase. So if you look at water, it can be a liquid up to the point of a temperature of 647.6 Kelvin. If you're higher than that, it's going to boil and it's going to be a gas, regardless of how much pressure you have. Now, if you're right at 647.6, you will have to apply over 217 atmospheres of pressure. Now, that water molecule is containing the most intermolecular forces of all of them in the chart. It has LD, it has dip-dip, and it has hydrogen bonding. The least critical temperature substance is nitrogen. It only has LD forces, and it has the lowest critical temperature. So critical temperature is a measure of intermolecular. Now we're going to look at another liquid property called vapor pressure. Now, some molecules on the surface of a liquid have enough energy to escape the attraction of the liquid, and these can move into the gas phase. So if you have more molecules in the gas phase above a liquid, well, what happens is that some of them start striking the liquid and turning back into the liquid. So the vapor turns into a gas, the gas turns into a vapor. Well, if you capture this in a container and measure the pressure of the vapor that's above the liquid, that's called the vapor pressure. And we've seen these pictures before. Looks like a little udiometer. And that liquid vapor is in an equilibrium. So the number of particles that are evaporating is the same as the number that are condensing. When you get this dynamic equilibrium existing, we consider that the vapor pressure. So if you heat up the liquid, you're going to have more vapor, you're going to have more vapor pressure. If you cool it down, there's less vapor pressure. So we're going to look at a chart on the next page of this. Continuing with our topic of vapor pressure and boiling, we're going to look at how you can get a liquid to boil. Well, liquids will boil when the external pressure equals the vapor pressure. So the temperature of the boiling point will increase if you increase the pressure. The normal boiling point for a substance is defined as the temperature at which it boils when the pressure is 760. That's the normal amount of pressure. So water will normally boil at 100 degrees Celsius. When you heat up the water, the vapor pressure of water reaches 760, and with the external pressure being 760, those two pressures are identical, and then the substance will boil. If you increase the external pressure on the water, its boiling point will increase. If you decrease the pressure, let's say you go up on top of a mountain, then its vapor pressure will decrease. Now the next little part that you need to know about the chart is the term volatile. Volatility, or saying a substance is volatile, just means that it evaporates very readily. So let's take a look at the chart. Again, we're looking at diethyl ether. If you look at the room temperature of around 25 degrees Celsius, diethyl ether already has a vapor pressure well above 400. It's like 500 or so. and that means it has a lot of vapor particles escaping the liquid. So if something is volatile, it readily evaporates. Now diethyl ether, with already a very, very high vapor pressure at room temperature, you only have to heat it up to 34.6 before it reaches the vapor pressure of 760, and therefore it'll boil. If you look at ethylene glycol, which is an additive to your antifreeze radiator in your car, it has a very low volatility. You want ethylene glycol to remain a liquid. You don't want it to boil in your radiator because your car will overheat. So ethylene glycol has a very low vapor pressure at room temperature. It is a low volatile liquid. The last little part is just the inverse relationship. If you have more intermolecular forces, you have a lower vapor pressure. And then if you have a lower vapor pressure, you're going to have a higher boiling point. Those are two relationships you will need to know. This graphical on the slide shows how you can measure the vapor pressure of a liquid. So in the first picture we have a vacuum above the mercury. The atmosphere pushes down on the bowl of mercury, which forces the liquid up into the tube, and it can reach a height of 760 millimeters. That is the normal atmospheric pressure. If you have a little bit of water above the mercury, the water will vaporize at room temperature, and it will create a pressure of 24 millimeters of mercury pushing down on the liquid in the tube. So instead of the liquid being at the normal height of 760 millimeters, it's 24 millimeters lower because of the water vapor pressure. If you look at the last picture, there's diethyl ether, and as we mentioned on the previous slide, it evaporates a lot, so there's going to be a lot of vapor pressure inside that tube, and it pushes down on the liquid with 545 millimeters of vapor pressure. So you can figure out the vapor pressure just by the difference in the normal height compared to the present height with that liquid above. Now there's two ways you can get a liquid to boil. The easiest way is just to raise the temperature of the liquid. That increases the vapor pressure, and when you get it to equal 760 torr on a normal day, then it will boil. The other way to do it is by decreasing the outside pressure. You could use a vacuum pump to do this. Now pressure cookers operate at high pressures, so you have an increased atmospheric pressure around the liquid. That means its boiling point is going to be higher than normal. And if you cook food using a pressure cooker, because the water is hotter, because its boiling temperature is above 100, then you will have a reduced cooking time. Now if you compare boiling points and molecular weights, again we can see that if you have a lower molecular weight for a compound, it's going to have lower intermolecular forces. That means it's going to have a higher vapor pressure, and it's going to have a lower boiling point. So those are some direct and inverse relations. This page just has some pictures of pressure affecting the boiling point. The picture on the left shows a volcanic vent. Now these volcanoes at the bottom of the ocean are under such high water pressure that bubbles can't actually form even though the liquid is above 100 degrees Celsius. So these volcanic vents are called black smokers, and they have water that's superheated. It's above 100 degrees, but it's not capable of boiling because the outside surrounding pressure is so great it collapses all the bubbles that try to form. The other picture at the top right corner is a pressure cooker, just showing you what it looks like. And there's an increased pressure inside the container, so if you put some food in there and you want to cook it in the water is going to boil above 100 degrees, and therefore it's going to cook faster. The last picture is showing you that you have different recipes. When you bake at high altitudes, you're going to have to alter the amount of liquid, maybe the cooking time, things like that when you're cooking at high altitudes, because the boiling point of the liquids are going to be less when you're up on top of a mountain. The next page shows an autoclave. This is a steam sterilizer device used in hospitals and veterinary clinics. My wife is a veterinarian, and she uses one to sterilize her instruments. It's basically a closed container. It's basically a pressure cooker on its side. You put in distilled water, it gets superheated, it produces such a high temperature that it kills all the bacteria that are on the medical supplies and surgical equipment that you place in the container. Now we're going to look quickly at phase diagrams. This is a topic that the AP curriculum has eliminated from their test. They actually said it's previous knowledge, which I'm kind of concerned about that because previous knowledge may mean that they expect you already know this stuff, but I'm going to cover it quickly here. This is a phase diagram. It shows the relationship between the three phases of matter at various temperatures and pressures, so it's just a chart with pressure on one axis and temperature on the other, and it forms a basic Y shape. The left side of the chart shows the solids where the temperature is cold, the middle part is where it's a liquid phase, and then the higher temperatures is where it's a gas. Now, every line represents a phase change. So we have the line connecting the solid and liquid. That's where you have melting and freezing occurring at equilibrium. Then there's a condensation evaporation line that separates the liquid and gas phases. Then down at the bottom, there's sublimation and deposition. That's where you have a solid turning directly into a gas, like dry ice sublimes, or if you go backwards, it's called deposition. Now, there's two important points on the graph. There's something called the triple point, where all three phases of matter are at equilibrium. Now, what that would mean is you could have the substance freezing and boiling at the same time, and I show a video of this in our notes, but all 6 phase changes are occurring at the same time when you're at the triple point. And the other important location on the phase diagram is called the critical point. The critical point is the highest temperature at which the liquid phase can actually exist. We mentioned this on a previous slide, but the graph actually stops at the critical point. There's no other liquid phase, it's just all vapor. So sometimes people call it a supercritical fluid, but it's a superheated gas. So it should be a liquid, but it's the pressure is not great enough to keep it as a liquid, so it turns into the gas phase when you're above the critical point. Now, this is a side-by-side comparison of the phase diagrams of water and carbon dioxide. On the left, you see water's phase diagrams, Y shape, and then on the right, you see carbon dioxide's Y shape. Now, the slope of the solid-liquid line tells you if it's going to expand or contract when you freeze it. If the line has a negative slope, like water's phase diagram shows, it's going to expand when it freezes, and carbon dioxide has a positive slope. It's leaning forward, and that means it's going to contract when it freezes. You can see that water vapor, or the triple point of water is a really, really low pressure that allows it to turn into a gas, and it's at a temperature right around the freezing point for water. So the triple point has a really low pressure and right around the freezing point. If you look at carbon dioxide's triple point, you can see the pressure is really, really high. That means in order for carbon dioxide to be a liquid, you have to have more than 5.11 atmospheres of pressure squeezing on it. Well, on a typical day, you have around 1 atmosphere. So if you have a block of carbon dioxide sitting on the table as the solid, that 1 atmosphere of pressure is going to allow it to turn directly into a gas. So there's the solid-gas transition down at the bottom of the graph. Looking at the carbon dioxide graph, that's around the point Y. So if you have a temperature of room temperature and a pressure of around 1 atmosphere, you're going to be in the gaseous phase on your phase diagram. Now, this next chart is just to show you the freaky nature of water. I said water expands when it freezes, which is true to some extent, but if you look at the red box, that represents regular temperatures and pressures. That's what the phase diagram normally looks like. But if you have extremely high pressures, we're talking thousands and thousands, millions times more than atmospheric pressure, well, the water can't expand, so it forms these different crystal shapes, and this is just how freaky the phase diagram becomes for the compound of water when you have extremely high pressures. So I just wanted to show that to you because I thought it was kind of cool. This slide actually makes the transition from Chapter 11 information to Chapter 12, so we're going to talk about solids and modern materials. So first we have to classify solids as either being amorphous or crystalline. Now, amorphous solids have no pattern to the arrangement of the particles, as you can see from the picture. They're just randomly arranged, and if you heat up a solid that's classified as amorphous, it's going to start melting over a wide range of temperatures, which means when you heat it up, instead of it turning from a solid into a liquid, it's just going to get softer and softer and softer and get more liquidy as you heat it. Some examples are glass, plastic, and wax. The crystalline solids, on the other hand, have a well-ordered, definite arrangement of the atoms. There's a pattern to this arrangement of the atoms, and we call that a crystal structure, this repeating pattern between the atoms or particles. And the melting point, therefore, is going to be at a very narrow range because all the connections between the solid particles are similar to each other. They have the same number and types of connections, so it's going to melt over a very specific temperature. So, for example, water has a melting point of 0 degrees. The examples of crystalline solids include metals, water, diamond, and table salt. We're going to further classify crystalline solids on the next slides. So now we're going to classify crystalline solids into 4 categories, and these properties that each crystalline solid has are going to be listed on the next slide, so I'm not going to spend a lot of time covering the properties. But anyway, the first crystalline solid is a molecular solid. It's formed from molecules. They have intermolecular attractions between them that makes them soft. They usually have a low melting point, and they can't conduct electricity because there aren't any charged particles that are free to move around in the crystal. Now, the intermolecular attractions are your LD forces, your dip-dip, and your hydrogen bonding. The second type of crystalline solid is a covalent network. It's formed by atoms covalently bonding together. Since that covalent bond between the atoms in the crystal are stronger than the bonding between the molecules, it's going to be harder. It's going to have a higher melting point. And again, you're not going to be a conductor if you're a covalent network crystal because you don't have charged particles that are free to move around. The third one is ionic crystals. They're formed from cations and anions attracting each other, so that's an ionic bond. They're also going to be hard. Not as hard as a covalent network, though. Covalent network is the strongest crystal bonding type, so it has the highest melting point. But ionic solids are stronger than the molecular dip-dip LD attractions. So anyway, ionic solids are hard, they're brittle, they're going to have a high melting point, and they're also poor conductors when they're a solid, but if you melt them, the cations and anions are free to move around, and that will allow it to conduct electricity if it's liquefied, or if you dissolve it in water, it can conduct electricity. Now, the ionic solids are brittle because when you alter the crystal structure, instead of having a cation next to an anion next to a cation next to an anion, you get 2 cations next to each other and they repel and it breaks the crystal apart. The last category is the metallic solids. They're formed from metal atoms, and their hardness varies because you can have soft metals like lead and pure gold, or they can be hard like titanium. And they have a high melting point, but mercury is an exception. Mercury is a liquid at room temperature. In fact, some of the metals have lower melting points like gallium, so maybe I should have said on this slide their melting point can vary. But in relation to a molecular solid, they're going to have a higher melting point. They're good conductors because they have valence electrons that are free to move throughout the crystal. I'm going to talk about the sea of electrons on the next page. And they're malleable, which means when you hit them with a hammer, they just spread out, they flatten, so you don't have charged particles that are interacting with each other. You have one atom. If you hit it with a hammer, it just moves next to another atom that's identical, so it's no big deal for it. So it just flattens out into a sheet. And they're also ductile, which means you can draw them into a wire. This page has all of the properties and intermolecular forces that I discussed on the previous slide listed in a very pretty chart. There's also examples, and I suggest you have some of these in your head when you're taking a test. Molecular solids, a good example is dry ice, sugar, water, things like that. Covalent network only has 2 examples, diamond and quartz. Ionic solids are your salts, and metallic crystals are any of your metals in the periodic table. Now I wanted to mention a little bit more about metallic solids. They are formed from metal nuclei floating in a sea of electrons, and there's going to be a diagram of this on the next slide. But their valence electrons from the metal atoms are considered to be delocalized. They're not really associated with any one individual atom, so that valence electron is free to move throughout the crystal, and then it makes the metals good conductors of electricity. Now, this slide has a picture of each crystalline solid. The top left corner are the molecular solids. The little dotted lines are the hydrogen bonds between the water molecules in this particular picture. A covalent network has all the different covalent bonds shown by the little sticks. We have the ionic solids with the positive and negative ions in a crystal lattice. And then we have the sea of electrons surrounding the positive nuclei of a metal. So again, when you hit a metallic crystal with a hammer, you can shift the positive the positive nuclei around, but the sea of electrons are still able to flow around the crystal so they can conduct electricity. Now I wanted to briefly talk about some vocabulary words that your textbook will use describing crystals. There's something called a unit cell, which is the smallest repeating unit of a crystal. And a unit cell has the symmetry that's related to the entire crystal. And when you pack these unit cells on top of each other, you get something called a crystal lattice. So the diagram shows a unit cell just being this block of atoms. Now the AP people do not have you learn about the crystal types for the AP test, so this is just bonus information. There's a question in your Chapter 12 homework that I put as extra credit, so I just wanted to briefly mention what the 3 types of unit cells are. So there's a primitive cubic unit cell. Sometimes it's called a simple cubic structure. There's a body-centered cubic structure which has an atom in the middle of this block of 8 atoms, and then there's something called a face-centered cubic structure, and you can see in the diagram why it might be called a face-centered cubic structure. There are 6 sides to the cube, and there's an atom on each face of that cube. So these are the different unit cells. Here's a random fact about molecular solids. We used to think that molecular solids would be insulators of electricity, but in the 70s we discovered some molecular solids that do conduct electricity, and that conduction of electricity was caused by delocalized pi bonding in the molecular solid. The example that was discovered was graphene or graphite. It's able to conduct electricity within the plane of the molecule, and that was an unusual property of molecular solids. Now, another type of molecular solid that you learn a lot about in biology class is polymers. Molecular solids are usually composed of small molecules, but when you make a polymer, they are composed of very, very large molecules. And there's some important commercial and biological applications, and we're going to look at those on the next slides. So here are some commercial polymers that we use in everyday life. Your low-density polyethylene. That would be your film wrap or your plastic bags. Then there's high-density polyethylene, and that would be for like bottles and toys and things like that. Then if you look at the list, there's PVC. That's the PVC pipes that you have in your house. There's saran wrap. There's polystyrene, which are packing peanuts, and it goes on down the list. So these are commercial polymers. Now each polymer has a formula, and there's something called a monomer. Those are the little bits that you add together to form the polymer. So those are called the monomers. And each of these commercial polymers, they're given a general name, maybe called plastics, but there's also some rubbers that are down at the bottom, and neoprene, things like that. But each one of these polymers have specific properties which are used in different applications. Now our biological polymers come in 3 types. There's carbohydrates, there's lipids, and then there's the DNA nucleic acids. So carbohydrates are in the category of sugars, starches, and cellulose. You take a monosaccharide, you start sticking them together, and you make larger saccharides like a disaccharide or a polysaccharide. So these are biological polymers. Then you have your lipids, which include fats, and then phospholipids and steroids. And you can see that there are 3 stearic acids that are stuck together along a glycerol backbone. So these are individual monomers, if you want to say, kind of stuck together to make a larger molecule. Now lipids don't dissolve in water. Things like fat doesn't dissolve in water because it's nonpolar, but your carbohydrates can dissolve in water like sugars. On the next page are your proteins, which are composed of amino acid monomers, and there's the primary amino acid structure, which tells you just the sequence of the amino acids that are used, and then there's a secondary structure which includes the alpha helix. So these amino acids kind of spiral together, or they can form something called a beta sheet. That's the secondary structure, and then it folds together to make a tertiary structure, and the way it folds is going to determine its properties. And then you can take some of these individual protein sections in the tertiary structure and add them together to form something called a quaternary structure. Now a lot of these are just biological examples. The AP people mentioned it in the curriculum that polymers are an application of molecular solids, so I just wanted to mention them to you. I'm not going to have you know too much about it on my test, but they do exist. The last little page shows the nucleic acid as a biological polymer. It includes DNA and RNA, and you can see the repeating structure throughout the DNA crystal. Here's a little more detail about a particular covalent network solid. It's carbon. Now carbon has something called allotropes. It's different crystal structures for the same atom. Now carbon can form graphite, which are flat layers of atoms, and each atom forms 3 covalent bonds, and it leaves 1 electron in the outer orbital delocalized, so it can conduct electricity within the plane. And the second type of allotrope, or the second type of crystal structure, is diamond. It's the hardest substance that's naturally found on the Earth, and it forms tetrahedral blocks of interlocking atoms. So if you rub graphite on a piece of paper, 1 plane of the graphite falls off of the crystal, and so you get, a pencil mark. But if you rub diamond on anything, it's going to scratch the surface because the carbon atoms are not going to break apart from each other. The last type was discovered much later than the other types. Buckyballs were discovered in the soot of a smokestack, and they're a soccer ball shaped sphere, and they're named after the architect Buckminster Fuller, and he's responsible for the Epcot Center down in Orlando, Florida. But buckyballs are a round ball-shaped crystal of carbon. Now there's another covalent network solid that the AP people want you to know about, and it's silicon. Now silicon is a covalent network exactly like carbon, which shouldn't surprise you because it's in the same group, and it's classified as a semiconductor. Now silicon forms the same geometry as a diamond, so it's also the tetrahedral shape. Now silicon's conductivity increases as the temperature increases, so the hotter you get it, the easier it is for the electrons to move around. Now, since it's only a semiconductor, we have to use that characteristic to help mankind by making transistors. So silicon can actually change its conductivity by doing something called doping. It's a fun little term, semiconductor doping. Now, periodicity can be used to understand why doping with a particular element changes the semiconducting property of silicon. So what doping is you take the silicon crystal, the pure silicon crystal, which is just your tetrahedral shape of silicon atoms covalently bonded together, and you remove some of the silicon and replace it with an atom that has one more valence electron or one less valence electron from the silicon. Now if you take one more valence electron, like somebody from group 5, that's called an N-type semiconductor, which gives it a negative charge because you have one extra valence electron that can move around through the crystal structure. And if you dope it with an element with one less valence electron than silicon, that would be something from group 3 like boron or aluminum, you form something called a P-type semiconducting material. And that P-type comes from the word positive, so it has a positive charge carrying capability. And there's something called a hole that forms in the crystal structure for the P-type. Now there's a junction that can be between an N-doped and a P-doped semiconductor, and that can control the flow of electrons through a circuit. And that's the basis of transistors. And to go into a little more detail about transistors, you need to watch the YouTube link shown below, and it's from a Veritasium YouTube channel, and he does an excellent job of explaining the difference between N-type and P-type semiconductors. Now this page shows a picture of N-type and P-type silicon semiconductors. You have the pure silicon picture in the middle. If you add a phosphorus, there's an extra electron, so it makes it an N-type. If you add boron, there's a hole, which makes it something called a P-type. And this transistor picture I actually copied and pasted from the YouTube video that I mentioned on the previous slide. So if you haven't watched it, you really need to. Our last topic in this unit is alloys. Now this is a new topic for me, for the AP curriculum writers. They wanted us to teach you a little bit about alloys. Now metallic solids are usually soft. They're usually pure substances, but they don't have the properties that we need them to have to make stuff. So we mix them with other metals and we make them harder and less malleable in some cases, and these are called alloys. So if you mix two solids together, you get an alloy. Now nearly all the common uses of iron involve alloy compositions. Pure iron by itself is not strong, it's not malleable enough, or it's too malleable. It doesn't have the characteristics of strength that you need to make, let's say, a bridge. Pure gold is too soft to be used as jewelry, whereas if you mix it with copper or even silver, it can become quite hard, so it has more useful properties. Now some properties of alloys can be understood in terms of the size of the component atoms in the alloy. So what you see in the picture on the right is something called an interstitial alloy. An interstitial hole is just a gap in the crystal structure between the atoms. Well, if you can fill in a smaller atom into those gaps between the larger atoms, you get what's called an interstitial alloy. Steel is an example of an interstitial alloy between iron and carbon atoms. The carbon fills in the gaps. Now that's going to change the properties of the pure iron. It makes the lattice more rigid, it's going to make it less malleable and less ductile, so it's a lot harder and it can be used to build bridges, where pure iron is not a good metal to use in a bridge. In some cases, an alloy can actually alter the surface chemistry of the metal. So an example would be stainless steel, where you're going to put chromium and nickel and of course some carbon into the substance, and that creates, the chromium especially, it creates an inert oxide layer so it doesn't rust. The other type of alloy is called a substitutional alloy, and that forms between atoms that have about the same size of the radius. So for example, if you look at the periodic table, copper and zinc are next to each other in the 3D row, so they have about the same size. So if you mix copper and zinc, you end up getting brass, which is a substitutional alloy. And the density of the alloy typically lies between the component metals. So if you have a density of 5 and you mix it with a metal that has a density of 6, you'll have the average density of the material. And the alloy is going to remain malleable, it's going to remain ductile, whereas the interstitial alloys are changing the malleability and changing the ductility. A substitutional alloy really doesn't do that. Alloys, again, typically retain their C of mobile electrons, and so alloys of gold and silver and copper and steel is still a good conductor, so we're not going to consider the conductivity of the material to change hardly at all. As mentioned before, metallic bonding can be represented as positive metal ions, and you got your valence electrons drawn on around them as a sea of electrons, and that's why the conductivity is not going to change. In the this electron C model, sorry about that, the electron C model can be used to explain why metals are conductive, why they're malleable, why they're ductile, and why they have a low volatility. That low volatility comes from the strength of the attraction between the metal ions with each other. The last slide of our unit just shows interstitial holes that exist in an ionic crystal. In a face-centered cubic crystal unit cell, there's actually more than one type of hole or more than one type of space between the atoms. So we're looking at the gray spheres representing one type of atom, and there's spacing in between them. Well, the octahedral hole is pretty easy to see where it is. It's on the edges of the crystal structure. The tetrahedral holes are actually inside the box that's drawn, and the ratio of the atoms in the picture on the left is a 1-to-1 ratio. So for every atom inside the box that is colored gray, there's one atom that's colored blue. So if you counted how many particles were inside this unit cell, you would get a 1-to-1 ratio, and that's how salt, the table salt, forms its crystal structure, where the sodium and chlorine are mixed together in octahedral holes. The tetrahedral holes are filled in a 2-to-1 ratio. So if you counted how many atoms were inside the unit cell, you would have 8 blues and 4 grays. And again, it's kind of difficult to see from the diagram on this page, but that's how calcium fluoride forms. The calcium would represent the it would represent the gray structures, and the fluorines are the blues. So I just wanted to show you that there's interstitial holes in metallic solids. There's also interstitial holes in ionic crystals. And that's it.